W to say X. Wait, I guess I'll just write it out, I guess. Hopefully I remember this right. So I believe if we have yeah, so that's just, so I guess that gives you a relationship when you, I guess kind of a generalization of what we do with the dual spaces, where each time when we take that we get a new norm for each system. This will define how we can get multiple iterations of the norm, I guess. Yeah. So a few other properties of these. So if we have, again, T is within the mappings from T to W. Then we can define its adjoint, T prime, and map V. So basically we have the adjoint operator T is within the space mapping the dual of W to the dual of V. And we then can...
Is it denoted by T prime or T star?
They use prime in some cases and star in others, actually.
Is there a difference? Usually it's denoted by T star. That's the adjoint.
I'm not sure. For this specific example, they explicitly called the adjoint T prime, and then I think on the next page they started using T star.
Maybe it's not consistent with the notation.
Yeah. I can. All right.
So how is it defined? How is it related to T?
Yes. So we then have the relation.
And what are these brackets?
I believe it would be inner product. I think they might have just defined this over Hilbert space. Yeah, they might have just defined that over Hilbert spaces. I'm sure I'd have to look at the book to be sure.
Well, what do you think?
I think...
Can you define an adjoint in a Banach space if there is no inner product?
I don't think so. I think
right, so adjoint is related to a particular inner product.
Yeah, so it has to be.
If you have one inner product, you get one adjoint. If you introduce another inner product, you get another adjoint. So it's just intimately related to that. So if V and W are Hilbert spaces, then you can define the adjoint by this formula.
Yeah, I must have missed that rule.
If you have to understand that these inner products are in different spaces, why don't you put indices? On the left, what is this inner product and which space?
Okay, this is the inner product of V, I believe, and this is inner product of W prime.
Well, look at the left carefully. TV maps it to where? V is in V. When you act with T on it,
TV maps it W.
W. So this is in W.
And that's in V prime.
That is in. Right.
Yeah. Okay. No, that's just.
No, that's right.
Yeah. Okay. Yeah. And then we.
Oh no, that's in V. No, that's in V.
Yeah. Right. Right. And we then have the other relationship that we can get there from, I believe it's the Han-Banach theorem.
Excuse me, well, I don't think you need primes there. The adjoint maps W to V without primes. Yeah.
And I guess so that we have the norm of an operator is exactly the norm of its adjoint. this also will not be the longest lecture today. Didn't have too much time. Didn't have quite as much time to prepare as I'd like. But anyway. So,
can you give us an example, say, of an operator on functional spaces, say, in one dimension, you consider, say, an operator on,
okay.
say, an interval or on a scalar line, and take a differential operator and compute its norm, or
Okay.
something like that, or even product. So what would be the norm of a differential operator?
No, it's eigenvalues. I'm not sure if it's norm.
What do you think? Okay, take I don't know, functions on the interval 0 to pi,
Okay.
and the operator to be a second derivative or negative second derivative. Just write it down. Like t is equal to whatever. Right. Okay. So and your space is no, put negative there because that makes it positive.
Okay.
So
Space.
yeah, the functions are say on 0 pi.
That is continuous functions, I assume. Or?
Smooth functions.
Okay.
0 pi. Okay.
Alright.
So why did you exclude pi there? Just
Okay. No reason, I guess.
so what are the eigenfunctions and eigenvalues of this operator?
Alright, let's see. That is then, so
What
the
do you need to
eigenfunctions,
solve, yeah?
eigenvalues are squared. That's just gonna be negative, myself.
Just write it. Why did you ignorate? Just write it down. Okay, what's the solution of this equation?
So that's,
And what are the boundary? Let's say we assume Dirichlet boundary at 0 at the endpoints.
okay, so,
V at 0 at the endpoints.
okay. That, problem. View.
Oh, there is negative sign.
Right. Right, so keep that over there. Yeah, so that's just, u equals sine cosine. Or,
Okay, just write it down. Must be.
And then there are constants here.
Yeah. Okay, put those constants, yeah.
Is it different constant for you?
Of course different, that's C1 and C2.
Okay.
Now you have to satisfy the boundary conditions so that 0 at the endpoints.
All right, so that is, yeah, okay, so that's just C implies C1 equals zero. So we then have Ux.
Why do you say C1 is 0?
Sine.
When x is 0, sine is 0.
Yeah.
So cosine is 1. C2 is
Right.
0.
Oh, wow. Okay.
So first C2 is 0.
2 is 0. Okay. So that is 1.
Why is it 1? I mean,
Well, it's, all right, it's general, isn't it?
just leave it there. C1 times sine, that should be equal to 0.
Okay.
And not at x, at pi. When x is equal to pi, just substitute
Yeah.
pi.
All right, that's.
Sine
Sine
square root of
pi.
lambda pi is equal to 0. Just
Yeah.
write it down. Okay, from this you need to find lambda.
Well,
What is sine equal to 0?
0 and pi.
That's it?
And 2 pi and pi.
So just
Right.
find it.
Okay. So lambda is n plus.
No, pi is already there.
Right.
Just write square root of lambda pi is equal to n pi, right?
Right. Wait. Yeah. So okay. So lambda equals n squared.
And n is what?
All integers.
Including 0.
Yes.
Okay. So now just write the solution. So C1 is 0, right?
Well, C2 is 0. Right?
Yeah, C2 is 0, right?
Move x is equal to.
Just label it by it.
Yeah,
U
U
and
and
X.
x equals
C1.
C1 sine n squared pi. Okay.
Why is it n squared? Square root of lambda.
Right.
And how did you get pi there?
Oh, because I'm not paying attention.
Okay, nx, okay. So, now can n be equal to 0? What happens if n is equal to 0?
Then the whole thing equals 0.
So that's 0, which means that n is not equal to 0, because that's a trivial solution. So n here starts from 1. 1, 1, 2, 3, and so on. Okay, so that's the solution. C1 is a normalization constant that you should normalize, right? So to make the normal is equal to 1.
Okay, so then just.
Okay, so now try to compute the normal of that operator.
Okay. The operator.
Well,
So the norm of the operator
that's
is.
the definition.
Yeah, so it's just 1.
Why is it 1?
Oh, you say he's thinking of when you define the.
Well, take an arbitrary function, act with this, let's take this Vn, okay? And act with t on it. What do you have? T Vn, just write it. T
Okay.
Vn is equal to what? Don't need to write x, just delete x. You don't need x. T Vn is equal to. No, well, come on. T is equal to negative d squared. Look,
Right.
just step
Right.
from the board. Look at the code. You went too close to the board. Over there, you see that t is equal to negative d squared.
Okay.
That one x, it's lambda. Lambda is 1 squared. So what do you get?
So that gives us a.
But you're solving it again. You don't need it.
Well.
Look at that equation. Do you see that equation? The very
Yes.
first. What does it say? The second derivative is equal to lambda.
Oh.
Lambda is n squared,
Right,
so that's
okay.
it. Just try that. This is equal to n squared un.
Okay. So t un is equal.
N squared un. Okay, great. So now